This is the video for section 8.2, homogeneous linear systems. So in this section, we are going to consider systems of the form x prime equals ax, where A is an n by n matrix of constants, and x is a n by 1 column vector. Since this treatment is going to be fairly similar, or at least analogous to the case of HLEX, we are going to present all of the material in 8.2 in this video, and then in class we'll get a chance to practice things. So from class, you know that our method of solutions, again motivated by what we saw in the case of HLEX, is that we would like to look for solutions to this system that are of the form x bar equals a vector k times e to the lambda t, where what we found in class was lambda are what's called the eigenvalues of A. So remember, they solve a very explicit polynomial, namely they are the determinant of A minus lambda times the identity matrix. So that's what we mean by an eigenvalue. So as we know, there are going to be three possible cases since we're dealing with polynomials here. First case, we can have real and distinct eigenvalues. Second case, we could have real eigenvalues, but some of them could be repeated. And the third case is we could have some complex eigenvalues. And as before, each of these behaviors will result in different types of solutions to our systems. So let's look at case one. As in the case of an HLEX, the real distinct eigenvalues is the easiest case. So the theorem in your book says that if we have n real distinct eigenvalues for our n by n matrix A, and then we have n distinct corresponding eigenvectors, so lambda 1 through lambda n are my eigenvalues, k1 through kn are the corresponding eigenvectors, then the general solution of x prime equals ax on the whole real line is of the form x equals c1 k1 e to the lambda 1t plus c2 k2 e to the lambda 2t, etc., plus cn kn e to the lambda n times t. Now case 2 is the case that we have repeated eigenvalues. And as in the case of HLEX, this is going to be slightly more complicated, and it becomes even more complicated given that the following two scenarios could happen. So let's suppose I have lambda 1 being an eigenvalue of A with multiplicity m. So remember when we solve our polynomial, we set it equal to 0. That means the factor lambda minus lambda 1 would appear with a power m in that polynomial. So the first case is that there exist m linearly independent eigenvectors, k1 through km, corresponding to lambda 1. And in that case, our life is nice. Our general solution contains a term of the form c1 k1 e to the lambda 1t plus c2 k2 e to the lambda 1t, sorry, this is a typo, plus cm km, that should be e to the lambda 1t. So we get terms of those forms all times e to the lambda 1t because we have m linearly independent eigenvectors. So the next case would be, what if we don't have m linearly independent eigenvectors? What if there's only one eigenvector corresponding to lambda 1? Then our life gets more complicated, and it's a theorem that you can prove that our general solution will contain terms of the form c1x1 plus up to cm(xm), where x1 is column vector k11 times e to the lambda 1t, x2 is k21t e to the lambda 1t plus k22 e to the lambda 1t, and so on. xm is of the form km1 t to the m minus 1 over m minus 1 factorial e to the lambda 1t plus, etc., k to the mn e to the 1 lambda 1t, where our k, I, j's are column vectors that you have to use the problem to solve for. And our final case is the case of complex eigenvalues. So if I have lambda 1 is alpha plus I beta is a complex eigenvalue with complex eigenvector k1, well, we have some additional information. We know that lambda 2 being alpha minus I beta is also an eigenvalue. And in your book, you can read sort of how the proof of this theorem goes. But if we let B1 be the real part of that complex eigenvalue, complex eigenvector, and B2 be the imaginary part of that complex eigenvector, then we can write two linearly independent solutions to our system. X1 is of the form B1 times cosine beta t minus B2 sine beta t, all of that times e to the alpha t. And another linearly independent solution is of the form B2 cosine beta t plus B1 sine beta t e to the alpha t. So those are the three possibilities that we can have, and we see things are more complicated for sure than the case of HLEX, but hopefully you can at least see the similarities to what we've done before, so that can maybe help you sort of keep track of the different possibilities. So let's see a couple of examples. Let's take a nice 2x2 case. So I would like you to, we have the system dx dt equals 2x plus 2y, dy dt equals x plus 3y, and I would like you to find the general solution. So step 1, you need to find the eigenvalues of the coefficient matrix A. Do that. Pause the video and do that now. You should have found that your eigenvalues are lambda equals 1 and lambda equals 4. So we're in the case of real distinct eigenvalues. Step 2, find the corresponding eigenvectors. Pause the video and do it now. You should have found that corresponding to lambda equals 1, you have an eigenvector of the form negative 2, 1. And corresponding to lambda equals 4, you have an eigenvector of the form 1, 1. So our theorem tells us that the general solution to this system is of the form x of t is some arbitrary constant c1 times k1, which is negative 2, 1, times e to the t, plus c2 times the vector 1, 1, times e to the 4t. Second example, find the general solution of dx dt equals x plus y, and dy dt equals negative 2x minus y. So again, please find the eigenvalues. Pause the video and do it. So in this case, you should have found that lambda equals plus or minus I. So we're in the case of complex eigenvectors. Complex eigenvalues and complex eigenvectors. Second step is to find the eigenvector corresponding to lambda equals I. So in the complex case, we just need to find one of these eigenvectors, and then we will take its real and imaginary component. So do that. And you should have found that k1 is negative 1/2 minus 1/2 I, 1. So the next step is to write k, or k1, in terms of its real and imaginary components. So its real component is negative 1/2, 1, and its imaginary component is negative 1/2, 0. Notice that the real and the imaginary part of our vectors are both real vectors. So the imaginary part is just the coefficients that multiply I. So our theorem tells us that the general solution is of the form c1 times the vector negative 1/2, 1 cosine t minus negative 1/2, 0 sine t plus c2 times negative 1/2, 0 cosine t plus negative 1/2, 1 times sine t, because beta in this case was 1 and alpha in this case was 0. So in class, we'll get some practice both doing more repeated and complex, both more real distinct and complex eigenvalues, and we'll also get some practice working with the slightly more tricky case of repeated eigenvalues.